Hello, everybody. I hope you're all doing well. We're going to continue our journey into mechanical vibrations by looking at single degree of freedom systems and multi degree of freedom systems. So, first of all, the abbreviations. Okay, so SDOF refers to single degree of freedom system. Okay, and then MDOF refers to multiple degree of freedom system. Okay, we will typically limit ourselves to studying 2 degrees of freedom system. So we will limit ourselves to 2 degree of freedom systems. Okay, but to start off the proceedings, we're going to look at a single degree of freedom system. Okay, so first things first. So single degree of freedom systems, and we're going to look at this from the perspective of mechanical vibrations. And so here is the basic idea. Okay, so I have a spring mass damper combination. Okay, so first of all, I have the wall here. Let me draw it as a larger wall. Okay, and then in this situation, I have a spring. Okay, this is the other end of the spring, and then I have a damping element which is attached in the following manner, as you will see. Okay, and both of these ends are connected to a mass, which I'm going to call as M. Okay, so here is the mass M, and then the stiffness of the spring is K, the damping constant is C. Okay, and then on this particular mass, I'm applying a force F of T. Okay, this force is applied as F of T. This can be any type of a force. For example, F of T can be a sinusoidal excitation. Okay, so for example, F of T can be some A naught times sine omega naught T, something of that kind. Okay, so this is an applied force. Now, a single degree of freedom system requires only one independent coordinate to completely describe its position at any point in time. Okay, so single degree of freedom system requires only one coordinate or degree of freedom to describe its position at any point in time. Okay, many positions, many things that we have been looking at in dynamics, simple pendulum or maybe even the compound pendulum, the equation of motion, they're all single degree of freedom systems. Okay, so in this particular situation now, I'm going to take this figure that you're seeing here. Okay, so I'm going to copy this and bring it down so as to look at okay, what are the things that I can make of this. Okay, so let's see. So here is the situation. Now I'm going to say that the system is starting at SCP in the position that is shown. Okay, so this is going to be my SCP. Okay, so let me move this mass so that it's aligned here. All right, fantastic. So this is the static equilibrium position which we have seen in the previous lecture. Okay, and from the SCP, I'm going to be measuring the positive displacement of the mass and so on as the force is applied. Okay, and likewise, you will also be seeing that there will be positive velocity which will be defined this particular way. Okay, and I just want to write the sign convention once again, as you will see here. sign convention. Okay, so this is the arrow that represents the sign convention. Okay, this vertical line here, yeah, let me put a mark on that. So the vertical line signifies the origin. For the mass at SEP. Okay, this is the undisturbed position of the mass. Okay, and then the arrow points towards positive quantity. Okay, and so what is the meaning of this? Okay, now the meaning of this convention, the arrow does not imply that the mass is displaced in that direction. Rather, it implies that if the mass is displaced in that direction, then it is assigned a positive value. Then the displacement is assigned a positive value. Okay, this is very important, and this is something that you'll be doing for pretty much all the problems from now on. Okay, and the same story holds for x dot and x double dot. Okay, so same sign convention for x dot and x double dot as well. Okay, and it's very easy to understand why x dot will be treated as positive if it is pointing to the right. This is because x dot is delta x by delta t, right? Delta t for us is always a positive quantity because we are moving forward in time. And so if delta x is positive, then x dot is also going to be positive. And delta x is positive if it points to the right. Okay, that's essentially what we are saying here. Okay, so that implies x dot and x double dot are also positive if we follow this sign convention that we have. Okay, so this implies that this is true for all of it. Okay, x dot and x double dot, and this is a must. Okay, if you are using a certain direction for x to be positive, then x dot and x double dot will also be pointing in that particular direction. Okay, so this is an important thing here, as you will notice. Okay, now what I have to do is the following. So the degree of freedom in this situation is only 1, which means the coordinate x is sufficient for me to describe the entire position of the mass. And one more thing I want to write is that the coordinate x, or the degree of freedom x, is the independent coordinate. Okay, x dot and x double dot are dependent coordinates. On x. That is, if I know x, then I can find x dot and I can find x double dot. Okay, that's the typical idea. So they are dependent, and x is the independent coordinate. Okay, this is also something that you want to keep in mind, and something that you've probably seen when we are doing equations of motion for rigid bodies earlier on, or for particles earlier on. Okay, and then one more thing you can also look at from the figure very quickly is that if the displacement of the mass is positive, the spring is in tension. If the displacement is negative, the spring is in compression. Okay, and it is quite possible that anything can happen at any point in time depending on the motion of the mass. Okay, all right. So now I come to the situation where I have, okay, this is the SEP of the system. I'm going to now draw the free body diagrams of all of these. Okay, the spring is going to be in tension for a positive value of x. I want to write that down as well before I move ahead and and start manipulating this figure here. Okay, so the spring is going to be in tension, for a positive x. Okay, all right, so now we have everything done. We're going to draw the free body diagram of the spring and the damping element as well. So I'm just going to grab all of these guys, both of them together. I'm going to copy it and I'm going to paste it down here. Okay, so as the displacement of the mass takes place, the spring is going to have a restoring force. Okay, one end of the spring is connected to the wall, the other end of the spring is connected to the mass that is being displaced, which means that end of the spring is going to continue having the same direction of the displacement as the mass. I just want to make sure this is fine. Okay, all right, this is the damping force. Okay, the damping force is also going to be pointing in this manner as we have discussed earlier. So this is the spring force, this is the damping force. Okay, then I have the mass itself, which will be drawn, okay, with all of these things. Just want to show it with the SCP as well. Okay, now we know that is the SCP, so this is where it starts, x dot and then x double dot as well, because the mass will also undergo acceleration. So I have the free body diagram of the mass, I have a force applied on the mass, which is F of t. Okay, then I'm going to have equal and opposite forces because the mass is connected to the spring and the damping element, right? So this is going to be an Fs and an Fd here. This is the free body diagram of the mass. I have to draw its kinetic diagram as well. Okay, so to draw the kinetic diagram, I'm going to grab all of these guys only and then paste it down here. Okay, and in the kinetic diagram I'm going to be drawing the mass times the acceleration of the mass. So this is going to be m times x double dot. Okay, so as you know from before, this is the free body diagram and this is going to be the kinetic diagram, and likewise these are the free body diagram of the springs. Spring and damper. Okay, so once we have all of that done, then what do? All I have to do is first of all write the spring force and the damper force. Okay, so Fs is k times delta x, which means this is k times the displacement is plus x minus 0, because I'm looking at the mass being displaced in the x direction as drawn. If the displacement were in the opposite direction, then it would be minus x, and then the force would be changing direction as well, okay, as applied on the mass. Okay, and F of t would also be changing direction, because that is when that will be happening, right? Otherwise the mass cannot just travel back on its own. Okay, so this is going to be k times x. Then Fd is going to be c times delta x dot, and this is going to be c times plus x dot minus 0, so this is cx dot. Okay, as you can see from the figure here. And then I can say that sum of forces on the free body diagram is equal to sum of forces on the kinetic diagram, okay, for the mass. And what are the forces? F of t and then Fs and Fd. Okay, so if I write this out, this is going to be F of t minus Fs minus Fd. This is equal to mass times acceleration of the mass. Okay, in this situation we are ignoring friction, so let me maybe make a note of that. So we are ignoring Coulomb friction in this particular scenario. Okay, and the geometry of the mass does not play a role as so much here yet. When you start having rotational motion, perhaps it's going to play a role. And the mass is also constrained to slide in the horizontal direction only. So if you want, you can maybe put a small dashed line here and say, okay, the mass is sliding this way only. It's constrained to slide this way. So let me maybe do that by drawing it on here as well. Okay, so there is no vertical motion, there is only horizontal motion that is permitted of this mass. And including vertical motion is not a big deal. That will just become another degree of freedom that we have. Okay, all right, so I have all of these. I'm just going to put them all together so that I have F of t minus k times x minus c times x dot is equal to mx double dot, and I want to bring this to a standard form and introduce you to some variables here, okay, very soon. Okay, so I'm going to rewrite this in the following manner: mx double dot plus cx dot plus kx is equal to f of t. Okay, so this is the first thing that we end up with. Now I'm going to do a couple of things. I'm going to define or introduce the terms, okay, introduce the following terms. Okay, the terms are f of t, I'm just going to call it as some constant b naught times y of t. Okay, this is some force times some magnitude amplitude times some time varying quantity, okay, y of t, okay, where b naught is a constant amplitude. Okay, and then I'm going to introduce another quantity which I'm going to call as omega n, which is going to be square root of k by m. This is called as the natural frequency of the system. Okay, and the third thing I'm going to introduce you to is called as the damping ratio zeta. Okay, zeta is c by 2 times m times omega n. Okay, this is the damping ratio. Okay, and what is the meaning of all of these terms? Okay, so of course omega n, omega subscript n, okay, this represents the number of times that the mass can oscillate per second about a cp in the absence of any external force or friction. Okay, so this is the represents the number of times the system, this is the mass, can oscillate about its static equilibrium position in the absence of any external force or friction. Okay, and the damping ratio zeta, okay, this represents the level of damping in a system. Okay, level of damping in a system. Okay, so now what I'm going to do is okay, after having introduced you to all of these particular terms, I'm going to take my equation of motion, okay, from here. So this is the equation of motion essentially. You can write this down if you want. This equation of motion, we're going to start manipulating it. Okay, so I have this here, then I'm going to start dividing through by m. Okay, so that I'm going to get x double dot plus c by m x dot plus k by m x is equal to f of t by m. Okay, and one can do several things. This is one way of manipulating it, or the other way of manipulating it is dividing through by the stiffness k. Okay, that is also another way of doing it. Let me first do it this way. If I do it this way, then I'm going to end up having x double dot. Now, hang on, this is x double dot plus c by m. Okay, this I can write it in the following manner. Okay, so I'm going to multiply and divide by certain things. So I see that zeta is written down there, right? So I multiply this by a factor of 2 and a factor of 2. Okay, and then I do omega n and then omega n. Okay, so that I end up getting something that you will see in a second. Okay, I already have c by 2 times m times omega n to define zeta, right? So c by 2 times m times omega n to define zeta. So I just leave this there as x dot. And then k by m, is going to be omega n square times x is equal to f of t divided by m. Okay, f of t, you can substitute this as b naught times y divided by m. So I'm going to precisely do just that. Okay, so this is going to be b naught times y of t divided by m. Okay, or I can write this as x double dot plus this entire combination, right, c by 2m omega n. I'm going to combine all of these terms together, and that's going to give me zeta. Okay, so that I'm going to end up having 2 zeta omega n x plus x dot plus omega n square x. This is equal to b naught by m times y of t. Okay, this is one way of writing the standard form. Another way of writing the same standard form is the following. Okay, this is also equally valid. I'm just going to divide all through by omega n square. So that x double dot will be divided by omega n square, which means that this will become 2 zeta by omega n x dot, and then this will just be x, and this is equal to b naught by m times omega n square is just going to be m times k by m. So this is just going to end up having k here. Okay, so this is y of t. This is another way of writing the standard form. Either one of them is used by people. Okay, these are called as the standard forms of single degree of freedom systems. Okay, the term b naught by k, I like the second form of writing it where the term b naught by k is present. This is called as the static sensitivity of the system. Okay, the term b naught by k is called as the static sensitivity of the system. Alright, so this is it for single degree of freedom systems. This is called the equation of motion, the standard form of the single degree of freedom systems. This is the governing equation. So I'm just going to copy this and bring it down here. Okay, so for a single degree of freedom system, the governing equation is the following. Okay, I guess I'm not going to have space to have all of it. Okay, so I'm just going to write it and leave it down here. All right, so this is for the single degree of freedom system. Now let's look at a 2 degree of freedom system and then see what happens. Okay, so multi-degree of freedom systems, just started off this with A, right? So I need to label that as B. Just want to make sure. All right, okay, so I'm going to look at B, multi-degree of freedom systems. Okay, when we have multi-degree of freedom systems, then we require more than one coordinate to describe the position of the system. Okay, so they require more than one coordinate to describe the position of the system at any time. All right, now in our situation, I'm just going to consider something very quickly. Okay, I'm going to consider two masses which are connected together by springs and damping elements and so on. Okay, so here is the figure that I'm going to write. I'm going to copy my figure from earlier. Okay, so that this will be useful. Look at this. I'm going to copy this and bring it down here. I'm going to get rid of some terms. Okay, I'm going to get rid of this term as yet. I don't need it. Okay, I'll be bringing it down here, so let me just keep it here. Then I'm going to copy this again. Okay, and then paste it down here so that I have two of these connected together. I'm going to have a force applied on each one of them. Okay, so I need a good way of applying the force. I'll just draw it here, and likewise for this as well. Okay. Maybe I'll bring it up here. Okay. So there's a force applied. There's another force applied. I'm just going to label them in a second here. Okay, so hang on and look at this. So this is going to be K1, C1, and then I'm going to say that this is K2, C2, and I'm going to have a K3 and a C3, okay, which is attached to the other side of the mass. Okay, so I'm going to copy that, paste it here, and then say I'm going to have another wall there. Okay, so this looks complicated enough for us. Then this is going to be K3 and C3. Okay, then I'm going to have a force that is applied starting from the SEP. So now I'm going to have two coordinates, right, describing the position of these. So I can call them as x1 and x2, and correspondingly their velocities will be x1 dot, x2 dot, and so on and so forth. Okay, so this is going to be x1 and then this is going to be x2. Okay, and if I look at it this way, then the force applied, of course, starting from the SEP, there's a force F1 of t, and then on the other mass there's a force F2 of t starting from the SEP, of course. Okay, so this is F2 of t, then this is going to be mass M1, this is going to be mass M2. Okay, so now I have two coordinates, x1 and x2. Okay, so in this case, two coordinates x1 and x2 describe are sufficient to describe the motion of the system, okay, or the position of the two masses at all time. Okay, the sign convention that is used is still the same. Okay, the vertical line denotes the origin of the masses, and when the springs are all at SEP. Okay, so sign convention is the same as before. Okay, vertical line denotes the position of the masses when the springs are at SEP. Okay, and once again it means that it is not as if the masses are displaced in that particular direction, but if they are displaced in that particular direction, then they will be assigned a positive displacement value, and likewise for velocity and acceleration. Okay, so likewise for x1 dot, x1 double dot, x2 dot, x2 double dot. Okay, all right, so this is the system that we have. Then I'm going to start drawing the free body diagrams and so on. Okay, I'm going to copy all of these guys, bring it on to the next page. Okay, my aim is to come up with the equation of motion for this system. Okay, that is the aim. This is a 2 degree of freedom system. Okay, so this is a 2 DOF. Okay, we want to come up with the equation of motion for this system. So I draw this system once again from here, and then I notice the following. Okay, for a positive x1, the spring K1 is stretched. Spring of stiffness K1 is in tension. Okay, for a positive x2, the spring of stiffness K3 is in compression. Okay, that's something that you can see. And lastly, for a positive x2 minus x1, the spring of stiffness K2 will be in tension. Okay, these are the things that we will be noting here, and it does not mean, of course, that if the arrow is drawn this way, it does not mean the masses are displaced this way. It means that if they are displaced this way, then this is the situation that's going to happen. So if the mass is displaced along the direction of positive x1, then the spring will be in tension. Otherwise, it will be in compression, depending on how it is displaced. Then I start drawing the free body diagrams and so on. Okay. So I still need my figure for that. And I'm going to look at each of these springs and so on. So let me grab this guy first. Then let me grab this set of folks here. I think I need to have all of them. And then let me grab this one here. Okay. Now the forces are not necessarily the same in all of these, so you've got to be careful. Okay, I'm just going to label the forces in the following manner. Okay. All right. So for each of them, I'm going to have the following. So this one is going to be a force Fs1. This is Fs1. One end is connected to the wall, the other end is connected to the mass. Okay, and I just want to make sure this is pointed this way. Once again, this will cause trouble later on when we are trying to draw straight lines and so on. Okay, then I'm going to copy this line here, then paste it. I'm just going to start bringing it to all of these. Okay, just saves me some trouble. Okay, just hang on and watch this. Watch the fun. I guess I did not do a good job there. Just wanted to bring it close. Okay, almost there. And two more, and then we are good to go. Okay, so now I got to start drawing the arrows on each of them. I forgot one more here. Okay. All right. Okay, so this is Fs1, and then I'm going to call this as Fd1, this is Fd1, this is Fs2, Fs2, Fd2, Fd2, this is Fs3, Fs3, then this is Fd3 and Fd3, and I don't intend to have these as equal to each other, so let me just bring this guy down a little bit. Okay, so that they're all not necessarily the same as the other. Okay, so maybe I want to do this as well. Okay, so this looks reasonable to me. Okay, this is the first set, second set, and third set, and then I can directly write the following relationships. In the first set, Fs1 is going to be k times the total displacement, which is going to be plus x1. Okay, depending on how the mass is moved, I'm moving it to the right, so I'm going to put it as plus x1. If it is moving to the left, it will become minus x. But then the direction of the force will change. Okay, so you got to be careful there. Okay, then Fd1 is going to be c1 times x1 dot. Then here Fs2 is going to be, watch this, k2 times the positive displacement of x2 minus x1, because one end of the spring is being displaced in the positive x2 direction, the other end, if it is displaced in the negative positive x1 direction, then the spring is going to get compressed. Okay, and likewise for Fd2 as well, this is going to be c2 times x2 dot x1 dot, and then the last one is Fs3 is going to be, watch this, this is going to be minus k3. Okay, so that's something that you want to be very careful about. Okay, so this is because the force is pointing this way, and so this is going to be minus k3 times x2, and then likewise Fd3 is going to be minus c3 times x2 dot, or if you do not want to do it this way, you can do it the following way. Okay, so you can say that, okay, hey, I'm going to get rid of all of these guys here, these arrows. I'm going to draw them in the opposite sense. Okay, so you can do it this way as well. Cut this off and cut. I wanted to show you both the ways, and the second way is the one that I'm going to be using. Okay, cut this off, and then I'm going to cut that off as well. It's a pesky customer. Cut that off as well. Here is what I can do. I can show that this spring is in compression and the damper is also in compression for a positive x2, which means that this is now going to be plus and plus. Okay, and this is the convention that I want to be using. Okay, so this is the set of spring and damping forces that we have for each pair of spring and dampers. Then I go ahead and I draw the free body diagram of the masses and so on. Okay, so let me start off with the mass M1. There's a force applied on this mass, so I'm going to grab all of this. I'm going to copy that and I'm going to bring it down here. Okay, so here is the mass x M1, and we of course have to say that, okay, this was the origin of this mass, x1 dot, x1 double dot. Okay, there is an applied force first of all that I want to draw first. So this is F of t or F1 of t. Okay, this is applied on the mass. Then what are the other forces? You see, this mass was connected to this spring system here, so I'm going to bring this spring, I'm going to copy that, and I'm going to paste it, and I'm going to move around a few things. Okay, so look at this. I'm going to bring this onto this side here, and then I want to bring the other spring, the one in the middle, which is also attached, right, to the mass. I didn't want to do that, but copy that, and I'm going to bring that down here. Okay, so that we can see all the forces that are acting on the mass. Make sure that this is aligned with the springs that I'm seeing. Okay, that's good enough. Then I start writing all the forces. Okay, here I'm going to have a force Fs1. Okay, then I'm going to have the force Fd1. And then likewise here I'm going to have Fs2, which is equal and opposite to what I have drawn there. So this is Fs2, and then I'm going to have Fd2. Okay, this is the free body diagram of the mass. And then I have to draw its kinetic diagram right underneath it, which I'm going to be doing in a second. So copy that and then paste that down here. Okay, and then the kinetic diagram says that since the mass is displaced in the positive direction, its mass times acceleration will also be pointing this way. And I got to do the same thing for the mass M2 as well. Okay, so let me grab this mass first and then change some of the subscripts. Kind of a routine idea, but I think it is still useful for us to see how this is done. Okay, I want to get rid of all of these subscripts, and I want to write this as 2, and this is M2, and I'm going to copy this and then paste it down here so that I have my kinetic diagram ready as well, ready to go. Let me start off with the kinetic diagram. That's the easiest of the lot, right? M2 x2 double dot. Okay, then I bring the other springs that were there next to this one. So that was the second set of springs which was present right next to this mass here. Okay, and then there was the third set of springs which was present here. Look at the direction of the forces. Okay, they are based on the direction of the positive displacement of the mass. Okay, so these are the forces. There is an applied force of F2 acting on this mass, F2 of t. Then I'm going to have Fs3 in the opposite direction, equal and opposite. This is going to be Fd3. Okay, then this is going to be Fs2, and this is going to be Fd2. Alright, so this is the free body and kinetic diagram of the masses, and then I'm going to start looking at how to write the equation of motion. Okay, so take the masses together. Okay, I'm going to bring this entire set here. I'm going to copy that, and I'm going to bring that down here. Okay, this represents the FBD. This represents the kinetic diagram, and it's very easy to see that sum of forces in the free body diagram, according to force balance, should be equal to sum of forces in the kinetic diagram. I'm going to assume this to be the positive direction. Okay, and if I start doing all of that, then I end up getting the following: minus Fs1 minus Fd1 plus F1 of t plus Fs2 plus Fd2. This is equal to M1 x1 double dot. Okay, then I start doing the substitutions. Fs1 was minus, so my k1 times x1. Fd1 was c1 times x1 dot. Then I'm still going to have f1 of t. fs2 is going to be the following. It's going to be k2 times x2 minus x1, and then I'm going to have fd2, which is c2 times x2 dot x1 dot is equal to m1 x1 double dot. Then I'm going to start rearranging things and start collecting the common terms. So I'm going to have m1 x1 double dot plus, look at this, I had a minus c1 x1 dot minus c2 x1 dot, so this is going to be c1 plus c2 times x1 dot. That's one thing. Then I'm going to collect the other positive terms as well, which is going to be plus k1 plus k2 times x. Okay, these are the positive terms that I'm collecting here, and then I'm going to write the remaining terms, okay, which I'm bringing onto the other side. So this is essentially going to be minus k2 x2 and c2 x2 double dot. Okay, minus c2 x2 dot minus k2 x2 is equal to f1 of t, and this cannot be simplified any further unless we have a knowledge of what's going to happen later on. Okay, we will use natural frequency ratios and so on when you're looking upon substitution of a harmonic solution. This is typically done in system dynamics, so we will not be doing this. Okay, so this is the equation of motion for m1. Okay, likewise I'm going to do equation of motion for m2. Okay, and this is one way of writing it. The other way of writing it is the following. Okay, they're both the same. Okay, so copy that and then paste it down here, and then the other way of writing it is by saying, okay, this is equal to f1 of t and then c2 x2 dot plus k2 x2. Okay, this is also the same thing. I'm just taking the negative terms and bringing them onto the other side. Okay, these are both the same. Okay, then I do the same thing for the mass m2. Okay, I'm going to go and grab that mass now. Okay, copy all of that. Free body diagram, kinetic diagram, as you know from before. Okay, we have already done the hard work for this one. Okay, then I just paste it down here. Free body diagram. This is the kinetic diagram, and then you obviously say that sum of forces in the free body diagram is equal to sum of forces in the kinetic diagram, and then you start putting all the forces up. So this is going to be minus fs2 minus fd2, then I'm going to have plus f2 of t minus fs3 minus fd3. This is equal to m2 x2 double dot. Do the substitutions. So this is going to be minus k2 times x2 minus x1, c2 times x2 dot x1 dot, k3 times x2 c3 x2 dot is equal to m2 x2 double dot, which implies that m2 x2 double dot plus c2 plus c1 times x dot. I'm going to write it in the first standard form, x2 dot, and then I'm going to have k1 plus I'm sorry, this is going to be c2 plus c3. I apologize for that. This is c2 plus c3. Okay, then this is going to be k2 plus k3. I'm still sitting in the second mass form. Okay, k2 plus k3 times x2 minus c2 x1 dot minus k2 x1 is equal to m2 x2 double dot. You can immediately see that this is one way of writing, or I guess this is f of t, I'm sorry, on the other side. This is equal to f of t. Okay, this is one way of writing it. The other way of writing it is the same as what I had shown before. Okay, where I take all of these terms, write them on one side, and then I bring the other terms onto the other side. Okay, this is now going to be f2 of t, sorry, plus c2 x1 dot k2 x1. Okay, this is the other way of writing it. Both of them are equally valid. Okay, and this will be the equation of motion for m2. Okay, this is the second mass. And then what you can do later on, we will not be doing this of course in this particular course, you can substitute what is called as a harmonic solution. A harmonic solution means that solution to some kind of a sinusoidal excitation. Okay, if you have your forces F1 and F2 as sinusoidal forces, cosines or sines, then you obtain what is called as a harmonic solution. Once you get the harmonic solution, then you can obtain what are called as the natural frequency and amplitude ratios of the 2 degree of freedom systems. This is something that we will not be doing in this class, of course. Okay, all right, so we come to the end of this section here. Very brief summary, of course. I want to do that. I want to point out a few things. So single degree of freedom, multiple degree of freedom systems, we will limit ourselves to 2 degrees of freedom systems. Okay, in single degree of freedom systems, you have the force applied. I have the spring mass and damper arrangement as shown. I started the SEP. This is the coordinate that is used to describe the motion of the mass. The sign convention, the vertical line points to the origin of the mass and the arrow points towards the direction of the positive quantity. Okay, and the meaning is that the arrow does not imply that the mass is displaced this way, but if it is displaced this way, it will be given a positive value. Okay, and likewise I follow the same convention for x dot and x double dot, and you have to do the same thing as well. Okay, you can choose what side is positive or negative, that is arbitrary, but if you choose x to be positive in one direction and x dot and x double dot will follow through as being positive as defined that way in that same direction. Okay, and this can be easily reasoned out as we had done in the previous quick review of an introduction to vibrations. Okay, now the coordinate x is an independent coordinate here, so it's a single degree of freedom system. When the coordinate x is positive, the spring is going to be stressed or it's going to be in tension. When it is negative, the spring is going to be in compression, which means the force F of t has to change its sign as well. Okay, it has to be flipped out. Okay, then I draw the free body diagrams and I draw the kinetic diagrams. I obtain sum of forces in a free body and kinetic diagrams, and I come to the equation of motion, which I write in the standard form by introducing the quantities as you are seeing here. Okay, there are a couple of ways of writing this in a standard form, one or the other, but the important thing is, if you're looking at the governing equations, right, look at this, all of the coefficients are positive, okay, on the right hand side. So this is very, very important. If you're going to have a system that is stable, right, all these coefficients have to be positive. Okay, for a stable system, stable dynamical system, all the coefficients corresponding to the coordinate of that mass are positive. Okay, and I mean by these terms here. Okay, so this one here, and then that one there. Okay, it has to be corresponding to its coordinate. Okay, corresponding to the coordinate of that mass, which is, in this case I have only one coordinate, which is x. But if I go to a 2 degree of freedom system where you have done the same thing here, I want to point that out. Okay, in this case as well, you look at this and you look at this. Okay, all the coefficients corresponding to coordinate x1 of mass m1 are positive. Okay, this is very important for you to realize. Okay, this is the characteristic of a stable system, and we will of course not look at stability and so on, but this is something that you will see later on. Okay, and I want to grab this and then write the same thing with respect to the other one. Okay, when I'm looking at the mass m1, the coordinate corresponding to the mass m1 is x1. I'm not looking at x2. Okay, likewise I can say that, okay, in this situation as well, I can write that, okay, hey, coefficients corresponding to coordinate x2 of mass m2. Okay, I'm not looking at x1. Okay, and I need to write this as x2 corresponding to the mass m2. Okay, so this is going to be x2 corresponding to the mass m2 are positive. This is extremely important to understand. For a stable system, this is always the case. Okay, it will never be any different. Okay, for a stable system, this is always the case. This is always the case. All right, and these were the equations of motion, one of them here and then one of them here as well. And this is the end of the 2 degree of freedom system vibrations equation of motion. Okay, and then later on what we're going to do is we're just going to take many other different types of problems and then try to come up with the equation of motion. The solution strategies and so on is something that you will learn in system dynamics, and we will not be doing that here. All right, thank you very much for your time. I hope all of you are doing well. Take care of yourselves. Bye bye.